I started my academic career. While I was doing my PhD at the University of Calgary in Canada, what I did was I also taught some courses there. One of them was Introduction to Civil Engineering Material. This is almost 8 years ago. So this is from my side. It's quite interesting that time flies so quickly. And then afterwards, once I finished my PhD, I did some teaching as the instructor for Bachelor of Science in Construction Project Management um, for at the Southern Alberta Institute of Technology. And this course was essentially one of the courses or one of the programs back then was the only PMI accredited program in Canada. Right now, we have two programs that are PMI accredited in Canada. Do you guys know what PMI stands for? No? So it's called Project Management Institute. It's one of these bodies that are quite popular, let's say, in terms of the professional designations that they provide. So if you see anyone having a PMP designation beside their name, that's from this accredited body. Now, they also accredit, let's say, course programs as well. That's in project management. So it's quite, let's say, standardized, has particular standards that it has to adhere to. Once it does, it could get accredited. So that was the program that I was involved in. And I was also involved in the accreditation process. And then I did some postdoc work at the University of Calgary from 2017 to 2020. And then I started as the endowed chair for digital engineering and construction here at the Karlsruhe Institute of Technology. And this was, we were thankful for the support from Goldbeck that basically provided the whole professorship with a good sponsorship so that we can actually establish this important and strategic field and hopefully create some important and interesting areas in this respect. Okay, so what about the academic and educational background? So I did my Bachelor of Science in Civil Engineering at the Sharif University of Technology in Tehran, Iran, from 2005 to 2010. There, I did some work on non-destructive testing and evaluation of aging bridges. We're going to get a bit more familiar with these as well as we progress through the course and the ideas and the technology. But literally what this provides is some information on how the structure is and how it's going to be behaving. As our infrastructure ages, what we need to collect some data from that, right? Once we collect some data, we would be able to identify how well this structure is going to be doing from what we're expecting it to do. And based on that, that provides us with an analytic. Using that analytic, we can make better decisions. Okay, so the whole idea of data collection, especially with remote sensing, will provide us with better data collection, and with better data, we have better informed decision that we can make. Okay, and this is more or less the theme of my overall research. My Master's of Science, I did it at the University of Calgary as well. This was from 2010 to 2013. And this was about ultra-wideband positioning using these tags. And hopefully we're going to have one lecture in the lab that my assistants are going to be providing you with some tutorials regarding these and how these instruments actually work, because I think it's important for at least getting some exposure to it. What this provides is essentially an indoor GPS. Hello. Why is that important? You have now an opportunity to use these tags and some of these receivers in known locations so that you can get the location of this tag relative to the locations of these receivers. Now, this is also another information that you can gather, right? And you can now utilize these for various different aspects. One of which I used, was for safety management. You can utilize it for, let's say, searching for misplaced item. You can utilize it for various different aspects, for instance, asset tracking and asset management, especially in construction projects as well. And we're going to be talking about some of the benefits that it could provide and obviously some of the shortcomings with respect to the actual technology itself, right? Then my PhD and postdoc was again in the same theme of collecting data automatically and in a remote setting. So we can minimize as much as possible this data collection in terms of the, let's say, manual side of it. We now have much more opportunities to get more frequent data, and that would provide us with better decision making, right? And this was for more or less optical metrology, specifically for laser scanners. We're going to talk quite a bit about these throughout our lectures and our courses as well. So some of these research directions, we talked briefly about the first one. How many of you guys are familiar with the Morandi Bridge that's essentially ended up collapsing like this? Yeah, you've seen it, right? So there are various reasons why obviously this collapsed, and there are some aspects with respect to, let's say, corruption and various different other sides of it as well. But one important factor here is that the data that were collected was not properly reflected to the decision makers to be able to make decisions on an effective and timely manner, okay? This is what we want to, as much as possible, avoid. We at least want to have a very good understanding of what data needs to be collected. And with that data that needs to be collected, what can we actually do with that data afterwards? So as an example, what I did here, so that we can prevent these catastrophes from happening, 43 fatalities, I believe. When you have aging bridges and infrastructure, what ends up happening? So you have designed an infrastructure for a particular life cycle, okay? 50 years, 100 years, depends on the type of design that you've had, okay? Now, what ends up happening with these? We have multiple different aspects and risks that occur. One of these risks is obviously deterioration of material, okay? Can you guys think of another possible situation? Let's think more in terms of population. When it grows, what ends up happening? Yeah. More used, exactly. So the design that you had actually anticipated, especially if it grows in a let's say, disproportional manner, what ends up happening there is that you're going to be having some problems with respect to not knowing or not have designed an infrastructure like this to actually service this large increase in traffic. Most of the infrastructure, let's say, especially in Tehran, let's say that is a city that's I believe right now has almost 20 million population. Anything that was designed, maximum designed for something in the order of, let's say, 2 or 3 million. And this by itself required a lot of data to be collected. With that lot of data that needed to be collected, then some decisions needed to be made. So as an example, you can utilize these rebar. And there are various different types of technologies. I'm just giving you an example of an infrared rebar detection to provide us with some information about where these locations of these rebars are, so that we can then make some other, let's say, assumptions on the material properties and the transfer properties of each and every one of the objects and elements on site. As an example, you can have a prediction of what these mechanical properties are going to be. Once you have this information, then you have to do another parts, right? Then you have to do some simulation to be able to see, okay, how well, basically you want to digitally stress test this based on the information that you get to see how well this particular structure is going to withstand the new information in terms of the load and various different aspects, okay? And that by itself would take us more or less, especially when it's done in a real-time manner or a near real-time manner or let's say some frequency, that now takes us towards a digital twin type of a situation, especially when we have a two-way ability to communicate and we can really simulate exactly what is happening on site in a digital environment. And then we can have some analytics for control so that we can, let's say, reduce a bit of the traffic that could go into this location if we're having some difficulties and problems, or we're having some issues with respect to the responses. They're going to be a bit of an anomaly, okay? So these are all to get us some data that we're going to be using as decision makers to make better decisions. In this case, is for infrastructure. We also have a more recent example as well in Dresden, right? The bridge, yeah. So the whole topic of digital twin and collecting reliable information and actually being able to simulate this in a virtual environment is becoming increasingly more important, okay? So in terms of ultra wideband, I'm giving you just some ideas on what we can utilize these. So for instance, you have a worker, I mean, one problem that could happen on construction projects is with respect to safety. An unsafe environment. One area is that if you have a worker that is getting too close to an equipment that they're not supposed to be too close to. What we're hoping to do is that we're going to be having some safety boundary. Why are we having some safety boundary here? So any instrument, and this is going to be another theme that we're going to be talking about throughout the lecture, any instrument, any automatic way of collecting data has some inaccuracies inherent to it. Some of these are random measurement errors, and some of these are systematic measurement errors. The whole area of geomatics engineering is designed to minimize as much as possible the systematic error side of it. But we always are going to be having some random measurement and some issues with respect to both bias, which is the offset, as well as your precision, which is more or less a random measurement error. And that creates some inaccuracies. That inaccuracy needs to be accounted for when you're doing any type of design. In this example, I'm putting basically a safety boundary that has to be a function of the error of that instrument, right? This error of the instrument now needs to be measured somehow. That's one of the areas that we work on to see and stress test these technologies so that we can see if these technologies are actually ready or not. The other aspect of it, let's say if you have an equipment, right? That equipment going forward or backwards, is there going to be a difference between, let's say, the safety boundary that you want to add to it? Let's think about a truck going backwards versus a truck going forwards. There's an operator that's operating this truck, right? Let's say we're accounting for the safety boundary to be more or less accounting for the errors of that particular instrument, right? If it's going forward versus backwards, would we just provide the same amount of safety boundary to it? Would we provide more, less? Any ideas? Yes.
Going forward, probably bigger safety boundary because the truck is probably moving a lot faster than when it's going backward.
So speed is definitely a factor. So thank you. So you added one factor, which is going to be speed, but assuming the same speed. Assuming, but thank you. That is actually a very good observation. Speed is also a factor. But let's assume, yes, Frederick.
It's less in front of the truck because it's
Yes, and that's what we call the perception reaction time. So if someone wants to, let's say, brake, there's essentially a whole host of methodologies from psychology that we can adopt to understand how long would it take looking forward to basically press on the brakes versus when you're going backwards. That all has to be incorporated in these. Why am I saying this? Not because you're necessarily going to do this, but because you have to understand if you want to stress test a new technology, you have to think about absolutely every aspect with respect to that, coming from different areas of research, okay? So as an example, we now have an equipment. The hypothesis and the idea is that if we can track these and we can predict it with some machine learning methodologies and AI-based technologies, can we potentially identify some potential collision? And what I utilized was a topic called fuzzy logic. Is anyone familiar with fuzzy logic or has any ideas? Okay, fuzzy logic is more or less, to just think about it very crudely, is how do you and I understand if I want to, let's say, instruct you, look 45 degrees to your left. Okay. What about 48.5 degrees? Right? It's a bit harder, right? So that's the whole fuzzy logic area. It's saying, okay, how can we understand, because we're humans, okay, and we're operating these equipment, even if we're going towards the industry 4.0 side of it, which we're now going out of it to add the human side of it, which is the industry 5.0. If we want to add that extra part to it, what do we have to do? We have to make corrections or make instructions that humans can understand. So if you go 45 degrees and I go slightly more to the left, that would give you a bit more idea. If that's too much, less to the right. More or less, you're going to go to a better area there. That's the type of logic and that's the type of reasoning that humans can understand a bit better than 95.5 degrees, here, or 42.5 degrees there. Okay? So that's the whole idea. If we want to implement any system and technology that humans can actually be a part of, we need to be able to implement strategies that humans can actually understand. So that's one area of fuzzy logic. For instance, if you want to use this, if you want to say, like you have to turn, 45 degrees, 42.5 degrees here, the worker is gonna have a brain fog immediately, and probably they're gonna run directly to whatever is going to be prevented there, right? So these are also all other aspects that need to be incorporated. And then oftentimes what ends up happening is that when we have an unsafe situation, we have a person going into a location that they're not supposed to be going. So if someone's trained every morning in these construction sites, you're going to have a training session or a safety, basically a brief that's the safety inspector is going to be going there and talking to everyone, talking about different expectations, unsafe environment, and each and every one of the people, let's say they're on the swing stage, they know how they're going to be operating the swing stage. They have been trained. Otherwise, they shouldn't be allowed to go there, right? So thinking of that side of it, if they are trained and briefed, normally unsafe environments or let's say safety concerns do not happen as much. One basically way that this could happen, which statistically has been a bit more significant than normal as well, is if someone is not supposed to be in a particular location and they are. That would create an unsafe environment. This way, if we have some boundaries, we now can say that we know exactly what the coordinates are, what the coordinates are of particular people that are supposed to be in particular locations are going to be as well. We can then identify which people are not supposed to be in that area. One side benefit of this is also for productivity, right? Because we also don't want many people that are not supposed to be on this task to be on that particular task as well, right? But it also indirectly also helps with hopefully minimizing that risk associated with that portion of unsafe and basically dangerous situation that occur that is related to a person or a personnel or a crew not being trained to be in a particular location or not supposed to be in a particular location. Okay, makes sense? So each and every one of these tries to mitigate a risk of one issue from not occurring or from occurring, let's say. So that's pretty much you can have that. And then these are very tiny tags. We're going to hopefully have one session, I think by the end of this year. It's going to be either on the 6th or on the 18th that you're going to be taking a look at this in December. So you're going to be observing, because we've recently installed and bought these as well. And what ends up happening is that you have a tag, and that tag communicates with these receivers that are installed in particular locations that we know. Based on this communication, which is through radio frequency, but a particular frequency of radio frequency that is called ultra wideband. So it's a type of technology that has a particular bandwidth, that is a large bandwidth, that helps us with something that is called multipath effect, which we're going to briefly touch base, but we're not going to go necessarily deep inside of it. But it's just good for you guys to know and understand why these technologies would give us better, let's say, accuracy versus something else. Why would these technologies not be able to penetrate through walls and through different types of, let's say, larger objects to also give us accurate results, even if we're, let's say, in the basement, right? And each and every one of these are related to attenuation. So how much of this is going to be absorbed per that particular, let's say, material that is going to be emitted to, and then how much of it is going to basically go through, and then through this, how much time is going to be wasted. And that is going to be accounted for, and then the inaccuracies are essentially based on that type of measurement. So this provides us with some understanding of how we can get locations of objects, locations of people, personnel on construction sites. More or less, the application of this is in indoor construction or in, let's say, asset tracking for indoor, let's say, factories or manufacturing plants related to prefabricated construction. This really helps with that. Right now, they're apparently doing some work with Mercedes, with BMW, to be able to get the different parts of that. That could directly be translated to construction for, let's say, even larger objects as well, while you're assembling different types of elements together and components together. Okay, so this is just to give you some ideas. And then for my other area is more or less automated monitoring and control. So this was a competition pool. This is actually one of the first real BIM projects and BIM collaborative projects that I works on in Calgary. This was 2017 that I collected this, or 2016 that I collected this data, but the project was approved much earlier than that. And this was one of the first projects that basically did a full-on common data environment in BIM 360 back there. So it was, and you can kind of see it's quite a beautiful structure as well. It's a competition pool. It's a full large recreational facility. But what ended up happening is that they noticed a bit later that when they built this, the slopes were not matching the slopes that were planned. And this gives you an idea. Okay, you can do all the planning that you want, all the virtual side of it that you want. That information needs to be relayed directly to reality. If it's not properly relayed, there's going to be a problem, right? And this is an example of that, despite all of these beautiful structures, much more complicated structures that were correctly installed and placed there, right? And when did they realize that? They realized it, I don't know if you can see it, I think it's a bit hard, but you can see that there's tiles here, and they had already placed the tiles, and then they realized it. So what they ended up doing is they had to remove those tiles there, they had to resurface the concrete, and at that time they basically brought me in saying, okay, collect some data from this to see that we, what else do we have to do? So I used some of the algorithms that I developed, and then I realized that other than the fact that we have some of those problems, so this is more or less fitting the BIM, or the BIM is not correct. I would say a digital model that you have onto this, because BIM, I'll talk about this a bit as well. It's an information modeling process, okay? It's a part of a design development stages that you have. So that's where you have different levels of development of BIM. It is not a model. Yes, we represent all of the information within a graphical, let's say, model, but the model itself is not BIM. BIM is the process there. It's important because then it doesn't make you guys confused. What this is basically a semantic digital model. That's what it really is. Then if you utilize the BIM process to attach different information into this model, basically the graphical information and the non-graphical information together, then you can utilize it for various different aspects, including optimization, and then later on, hopefully for digital twinning as well. But I digress. What you got here was that we registered these together, and then we have basically some inaccuracies there as well. What ended up happening here is that other than the fact that these slopes were problematic, we also had these lengths that were problematic. So these were supposed to be, I believe, 25 meter or 50 meter. I think it was 25 based on the dimensions. So these are competition pools, 25-meter competition pool, 2 centimeters, 3 centimeters here or there. What's going to happen in a competition? This side versus this side, 2-3 centimeters here or there? Any ideas?
Probably enough. That's the one on the left side will always win.
Yeah, always win, or maybe even beats like world records, right? Like that's also another side of it, right? So here the dimension becomes very important. The relaying of that also becomes important, but also to identify this earlier on. Why? Because we want to identify as much as possible any type of changes that we need to make and any type of rework that we need to make as early as possible, where we have the most amount of degree of influence and the least cost of influence. So this is what we call the cost influence curve. Have you guys ever heard of this? Yeah. It's a very common sense cost influence curve, especially when you have activities or objects that each of them depend on some other prospective future object that is going to, or anything that is going to be built. You're going to have a situation like this. If these are completely independent, then yeah, there's not going to be, if something is problematic, then it's going to just be that linear, that one, let's say, problem that needs to get fixed here. But if these are dependent upon future steps, and in construction, more or less, a lot of our activities are dependent upon each other, this is what's going to happen, okay? So what does this mean? That means that as the project lifecycle increases, okay, our degree of influence on whatever change that there is going to reduce, and that cost of any change that we decide on is going to increase. This is more or less for areas of change order management and various different aspects, but it directly relates to rework due to poor construction as well. In this case, as an example, if we were to identify this much earlier on, we didn't need to come and bring all of those tiling crews. Then we had to remove the tiling crews. Then we had to bring the concreting crew as well to redo it, and then again rehire the tiling crew as well. So other than the fact that we have to now fix all of these, we have to also hire and fire different types of crews. Each and every one of these, it starts accumulating and exponentially increasing. We want to prevent this as much as possible. So this is where automatic data collection, as frequently as possible, could improve and help with the analytics that we need in order to make better decisions on a timelier fashion, okay? So this was the whole idea. We get some optical instrument like a laser scanner to collect some point clouds. Then from that, we have to process it. Really, the main gap is here between you have all of these points and all of this information. How do you automatically extract all of the information that you need from this as accurately as possible for our analytics? We actually have very good methodologies for the analytics side of it by itself. From prediction modeling, from statistical analysis, we have very good methods that are more or less what you're also seeing in let's say, with graph neural networks and with general frequent subgraph mining, and essentially anything related to social media and the prediction of, let's say, patterns and behavior. We're very good at that. It's years of research. Where we want to really minimize or we want to use is we want to bridge those gaps between whatever data we collect and whatever information we need in order to make those analytics or utilize those methodologies for construction analytics that we already have from different industries, okay? So this was just to give you an idea. This part was really to gather that information properly is where the main research gap was. And hopefully, if you guys get interested in continuing with the field information modeling course, that's going to be more or less your the topic that you're going to be working on. And then you have the automated visualization, and then you can visualize more or less what the problems could be. In this case, I talked about, I believe, for instance, for progress, we can have it in dimensional compliance, we can have it in structural deformation and various different aspects. But we need to know what we want on the other side in terms of the outcome. And then we need to see what type of data we need or what type of analytic we need and results we need so that we can map these two together and then make better decisions.